Hey everyone, welcome to my talk about Spark and Cassandra. How's everyone doing? Is everyone enjoying their Spark Summit? Yes? No? I mean, sorry, is everyone enjoying the Spark Cassandra Summit? This is really confusing because, believe it or not, there was a Spark Summit at the exact same hotel, like right here, like just 2 months ago. So, and I don't know, I might have even talked in the same room, but I'm not really sure. But that added to confusion. But, so, you can't hear? Can everyone hear? Is this okay? Okay, cool. All right, so yeah. Okay, so my name is Evan. I'm at Socrata, and I've worked with Spark and Cassandra for a number of years. I'm relatively active in the Spark community. I also know a lot of people in the Cassandra community. So I am very thankful for my employer, Socrata, sponsoring me to be here. It's really exciting to work for a company that what we do is that we built a online platform to make data useful to citizens, public data. So this is the city of San Francisco. They're a customer. Let's say that you live here or you live in San Mateo. How many people here live in the Bay Area? Cool. So if you're from here, San Francisco or San Mateo County or Alameda County, or you live in California, you can go to the websites and find pretty useful UIs as well as REST APIs that allow you to query the data and find out where your tax dollars going, or is the state of California doing well on their environmental things that they said that they would do. And this is tremendously useful for you as a citizen, and this is something that we do, and so we're very proud of our work. You can see that most of the biggest cities in the US are also our customers, including LA, New York, Chicago, DC. Like if you want to find out is your healthcare costs here comparable to other healthcare costs for certain procedures, you can find that out. So just really good stuff. So what are we here to talk about today? We are swimming in data. Of course, that's why you're all interested in Cassandra, right? At Socrata, we have, it's at tens of thousands. I think this number is at around 80,000 today. I'm sure it'll be at 100,000 data sets. Each data set could be in the millions or many millions of rows. So we're talking about a lot of data in aggregate. Our customers are demanding bigger and bigger data sets, especially at, say, the federal level. They're talking about billion-row data sets. And they want to be able to query this data quickly, right? How do we enable that at scale? Pretty hard problem. We also want to analyze across these data sets. At my last employer, Uyala, every time you watch a video, you receive data, right? You're talking about billions of events a day. Even when you do a roll-up table, that roll-up table is 30 million rows a single day. And customers typically ask queries like, how do we, what is the rate at which people watch videos, across regions for a whole year, right? The whole year, you can do that math, 30 million times 365, right? So, pretty serious challenge. The problem with designing for different kind of queries, traditionally in Cassandra, you think about, okay, what are the ways that people query, and if they query in a fixed way, I can store my data such that it's easy to query, right? That's typically how you use Cassandra. But sometimes that's not enough. For the kind of use case that we're talking about at my current company and probably for a lot of users, you need to do more complex queries. And just being able to denormalize your data to store it maybe 2 or 3 different ways is not enough, right? If you think about traditional databases, there's infinite ways that people can query the data. You want near real time, right? You don't want people to wait a long time before they can query new data. So let's look at some solutions that people have traditionally used for doing this, solving this kind of problem. RDBMSs, right? The standard solution for many, many years. For the kinds of latencies that we want for people to be able to interactively query the data, you start hitting latency limits pretty quickly. Like for us, I don't know, that number is, it's in, say, like 10 million rows range, like plus or minus something. Obviously, like if you're willing to wait like minutes or hours, you can have arbitrarily large up to a certain point. But for our use cases, that doesn't really work. Another problem with the RDBMSs is that there isn't really a good, robust way or inexpensive you can pick, for scaling horizontally. You might want to shard your data. That might work for certain use cases. If it's a user database, OLTP, that kind of stuff. If you're doing OLAP, that is a lot more of a pain. Postgres has a partitioning mode now. It's a pain to use. Another scaling problem is that Postgres will run your queries on a single thread. There are some newer solutions that will now do it on multiple threads or even multiple nodes, but those are pretty immature. Postgres XL, if anyone's heard of that. So what you end up having to do is you end up having to do a lot of work to optimize your tables, or you can create roll-ups. You do more and more, you put more and more man hours, man months into doing this kind of thing, and it ends up making your application more and more complicated, right? So that's not really the way to go. Another way that's been pushed since the mid-90s are OLAP cubes. And you probably know a lot of vendors that are doing this, everyone from Microsoft, Oracle. It's the cube command, and it will generate a giant. If you imagine that you have n columns, right, and they're all dimensions, maybe one is, say, city, right, and another is, pick some demographic thing like gender or something else. So the idea behind cubes is that you can generate an n-dimensional cube, and each dimension is one of the columns. Then you can aggregate that at different levels. At the finest level, in each microcube, that's like the intersection of all different dimensions. And then you would do a slice, which is like one less dimension, and so forth. So this is essentially calculating every single possibility that you could ever possibly query and storing that. And there's been like hundreds or, thousands of papers published as far as how to do this efficiently and stuff, which is great. But it takes a really long time to calculate this cube. It is really complicated. Like, God forbid anything should go wrong with it. Like, probably very few of us, unless you've done one of those papers, will really understand how to debug it. So it doesn't work for real-time scenarios. It also explodes your storage. So, and as we get more and more data, doing this, exploding, it doesn't really make sense, right? Like, cubes grow with respect, exponentially, or is it exponentially? Or depending on the number of dimensions, yeah. It grows superlinearly with respect to the amount of data you have, right? So what can we do? So Ken Thompson, who wrote C, said, when in doubt, use brute force. And in fact, what you talk about Hadoop and Spark, it's essentially this is the way that the world has moved, is towards using brute force. So what am I talking about specifically? You have Cassandra, which we all know and love. So we want to combine it with Spark. I don't really need to talk about this slide. I can probably skip it. But as you all know, Cassandra is horizontally scalable, pretty easy to operate. You don't have to worry about how many documents or rows. You just store data, and it just works pretty well. But it only works for simple queries, right? So in SQL, you can do a select. You can pick a subset of your columns. You can use a where clause to limit your data if you have secondary indexes and stuff. That's all good, but let's say that you want to do something more complicated. You want to find out the top 10 of a certain category. You want to do group bys. You want to do joins. You can't do any of that natively in SQL. Spark, I imagine most of you have heard of this, so I probably don't need to go through this very much. But Spark is a horizontally scalable in-memory. You can think of it as an in-memory Hadoop. It's a general, but it's a lot more general. It's basically, you can do a directed graph of any kind of computation. And you have functional transformations like maps, filters, group bys, joins. And it integrates a lot of modules, including an SQL layer, a streaming layer, machine learning, graph, R. It's actually amazing how many new modules are popping up in Spark and how quickly people are developing them. It's pretty much the hottest thing in big data right now, right? And everyone I know that's dived into it really loves developing with it. I mean, just the fact that, for example, you have a simple shell, you can go in there and you can experiment with it is, it's really, really nice. And I think, or rather, DataStax thinks Spark provides the missing analytics piece to Cassandra. So, how do you integrate Spark and Cassandra? You guys have probably heard of the Spark Cassandra connector, which is a super easy way to connect the two. If you want to write jobs using Scala, Java, then that's a really good way to go. There's another open source project that I listed. This might not work for everyone. You might be on a really old version of Cassandra, like 1.1 or something, or 1.2 where SQL just came out, and so maybe the Java driver is not an option for you. But that's not to fear. Spark will let you read from any Hadoop input format, as well as you can directly read using a Cassandra client. I removed code because I didn't think that, I imagine most people are probably on the newer version of Cassandra with CQL, but it's also like, for a long time we worked with the option to, I've done both. We've written our own input format to read from Cassandra because it's more efficient. And at that time, and this was before the new Spark Cassandra connector came out, and it's also pretty easy to read directly using Cassandra client, because in Spark what you can do is I can take a bunch of row keys and then spread them out and transform them into data by doing reads on each node, so which is pretty easy. If you're interested in that, you can let me know, but I would assume that most of you are probably okay with CQL, Spark Cassandra connector. So let's talk about an architecture for Spark and Cassandra working together for OLAP workloads. One of the first principles is that you want to separate, it's good to separate your storage and query layers. You're combining a best of breed storage and query platforms. What I see a lot of in the big data space is that you see a lot of for example, there's, I don't remember all the names out there, but for example, React has a built-in MapReduce solution, right? And then some of the other databases, there's a lot of these distributed SQL, like new SQL databases. There's something called Foundation DB, and then there's so many of them out there, and they're all designed to replace the data store. But what about just combining like two open source projects that are getting a lot of momentum, Spark and Cassandra? That way you can take full advantage of each one. You don't have to worry about, well, I'm missing this feature, that feature, because people are adding tons of features to Spark and Cassandra, right? And one neat thing is that instead of, let's say that you want to scale your query workloads, you have like a hot piece of data that's located on, in one place in Cassandra. Well, if you separate your query and storage layers, you can actually load that hot piece of data into multiple Spark instances or nodes, and you can instantly grow your query workload. I mean, there's some other issues with that, but there's a lot of advantages to separating out your storage and query layers. This one is pretty obvious, right? We want to, this is just basically like in a traditional solution like, RDBMS is like having to invest more and more time into customizing a solution. You just want to scale your nodes, right? Usually that's cheaper. Talk a little bit about keeping things simple. One main idea is to try to maximize. We keep things simple. Like instead of building like a lot of complex indexes, we try to make things efficient. So one way is an efficient file format, or in the case of Cassandra, an efficient way of storing data. We'll go into that in a little bit. Another thing to do is you want to maximize your scan speed. So ultimately, like if you talk about Hadoop or Spark, a lot of what's going on is that you're doing essentially full table scans, right? And so you want to maximize that. But the good thing is that that is being, like people are working on that and it's getting faster and faster over time. In the meantime, you can scale your nodes. When it gets faster, you can decrease your nodes, so it gets better over time, right? Whereas you spend more work working on really fancy solutions, then that's tech that you have to maintain, for a long time, right? I'll go into columnar representation later. You can achieve a lot of good compression that way. So this is a simple diagram that basically the one way you can do it is that you can use Spark as a cache for Cassandra's data, and then in Spark you can run complex queries on the data. So basically, initially you would load the data into Spark. This diagram assumes that you cache the data in Cassandra. I'll go over that a bit later. The way that Spark works by default is that when you read stuff from a source such as Cassandra or XGFS, it will, and if you don't cache it, it will subsequently keep reading from that same source. If you cache it, it ends up in the heap of the Spark workers. They're called executors, and that's basically what you see in this diagram. The problems with this approach is that when you cache it in a heap, then what happens if the process dies, right? So a slightly better idea is that you can cache stuff using Tachyon. So Tachyon is a Spark subproject which is designed as, it's kind of like an XGFS, or it's like an in-memory storage layer accelerator. So it's designed to pull data from your storage layer, cache it in memory, but it's off-heap memory. So that data can now be shared by multiple Spark workers, and even if one dies, you can reload another one, and you don't have to reload your data. So we did an initial attempt at all these different approaches. This is a bit of Scala code, and what this does is the first part basically loads up data from somewhere. In this case, it is just from memory, but that parallelized would be replaced by a call to, say, the Cassandra connector, which is called Cassandra table. And you can see that we're doing a map where you're reading in a row. The row has multiple values in it. And what we do is that we're mapping it into a grouping where we're pulling out the first column, which is values 0, and using that as a way of grouping. Then you do a group by key, which basically groups by the first element of a tuple, which is the value 0. And then we're doing a reduce, which is to sum things up. So this is a really simple like count, a summing grouping aggregation example. This works fine, but there's some things that are wrong with it. Performance-wise, there's a lot of, so when you store data this way, especially for doing numeric aggregations in a JVM, you end up boxing every integer. And the reason for that is, well, if you know, there's ways to get around this, but in general, if you want to work with many different types of data, you end up having to do, in Java, this would be like a list of objects or something, right? So you end up having to box data of different types of integers, doubles. Does anyone know how many bytes of memory, the minimum amount of memory you need for a Java object in memory? It's actually around 20-something bytes, right? Because every object has to have certain header information in the JVM. So it's actually extremely expensive, not only for memory use, but if you're adding up 10,000 numbers or a million numbers, then every time you have to kind of unbox that number, get it, point it to reference, add it up, do the next one. So it's extremely expensive, right? This operation. So a slightly better way is to look at the columnar orientation, columnar storage and querying. Does anyone know who Michael Stonebreaker is? Yeah, he's the founder of Postgres, Ingress, and like a lot of the huge data, like one of the foremost data experts. He said the traditional role-based data storage is dead. The traditional way that you store data is that you store it with all the data from one row together in memory and also on disk. So all the columns in row 2 come up to row 1, right? So this is pretty obvious to everyone. In a column-oriented storage, what you do is that you store the column, all the data from one column together. For example, let's say you have a name and an age. The name one is stored using a dictionary. So each string would be represented by a number, and we would store that together. So in this case, what we're storing is Barack and Hillary, but we're actually storing 0 and 1, which for most data types which have much less values than the number of rows, this saves a huge amount of space. And for the age one, is pretty obvious. Now, how would I do this in Cassandra? So what you would do is, let's say that I can have a schema column family. All this is doing is for each column, I'm going to store the type. And maybe there's some extra metadata, like if for string columns, I'm going to need to store a dictionary. And in the data column family, what I'm going to do is I'm going to store a physical row, or you can think of that as like the first part of the partition key. I'm going to store a column of data, but in a physical row. The reason is that in Cassandra, all the data that belongs to one partition key, that belongs to one physical row, is stored together on disk. So you can read that data out very quickly. And this gives you opportunities to apply some of these techniques, such as dictionary compression, things like that. And so you see the name and the age are stored together. And this is not the most optimal way to do it, but the most simple way to do it is that you can say store one value per column. You would most likely want to batch it together so that you can store like multiple values together. But it's a kind of a trade-off. For some people, they might want to update the values, for example. So the advantage that you get is that you get a huge amount of compression, and you minimize your I/O because most kinds of OLAP queries only read out a subset of all the columns. So this way, when you store data, let me show this again. So when you store data like this, then I can read data out. I can only read the rows that I'm interested in instead of having to read all of your data, which you would need to do if it would be much harder to pull out the subset of data in the traditional row-based storage. It would be a lot more inefficient because you're trying to pull out tiny bits of a lot of data versus in a column-oriented way, I'm pulling out a big chunk of just the columns that I need. And you can avoid the boxing overhead because now I can store data in their native types. Basically, each column is strongly typed.
Could you
Question?
give an example why performance one is much better than the other one?
I don't have specific numbers for. Actually, I do have some rough numbers. But is that what your question is about?
Yeah, I'm always confused why one performance is always much better than the other one. Column-based is much better than row-based.
Well, it's not. I wouldn't say always. I mean, there's. I would say for most OLAP workloads, it is better because you're pulling out a subset of columns. Like there's a lot of data sets that, for example, have like 50 or 100 columns. And a lot of times, let's say that I want to find out I mean, it depends on data set, but let's say that I want to find out the top 10, I don't know, countries, right? Then I only really need, by something else, I only really need 2 or 3 columns. And so I can pull out just those columns, and my I/O is immediately like decreased by 10x, right? And that's aside from the benefits that you get from things like dictionary compression, where you can store like you mentioned, list of strings. The naive way to store strings would be just to store string, 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 string. Let's say that I have 1 million rows, right? And I actually only have 10,000 strings, which is pretty typical for most data sets. So what I'm talking about is storing, you can represent 10,000 different values using 2 bytes. So I'm talking about using 2 million bytes to store that data versus 1 million times, I mean, however long those strings are, right?
Basically, strings are more expensive from a storage perspective.
Strings are way more expensive. It's not only the storage, right? So you can also query data in a columnar way. And so you can ask yourself, like, is it faster to compare 2 strings or to compare 2 integers? Right, that's pretty obvious, right? So if you execute a database query in a columnar way, you can get huge benefits. Let's say that you're summing up 1 million numbers. Most processors have a very small level 1 cache, like maybe 64 kilobytes or something. And each cache line is like maybe 64 bytes. Now, if I have to read a row-oriented data, most rows already exceed 1 cache line. And so if I have to add up numbers from multiple rows, you're constantly like flushing out your cache. If I'm adding up numbers in a columnar way, I can pull out 16 4-byte integers into the cache line, not have to replace it and sum it up. It's really, really fast. Right. So so we did a study of a columnar query engine versus a row-based one in Scala. In Spark, I don't have enough time to explain exactly how it works, but this basically used about 10 times less heap and was like 100 times faster in terms of aggregations. So great, OLAP with Cassandra and Spark. Now what do we do, right? So we'll get the party started. As I mentioned before, like there's a Spark Cassandra connector, and DataStax is rolling out an XA version of Spark with an XA master, which is really cool. Spark has an SQL module, which is new in version 1.0. Spark is about to release 1.1. It comes with an in-memory columnar store, which is pretty cool. It has all the benefits that we talked about before. It can read from Parquet and JSON files right now. They're adding CSV support and direct integration with other data stores.
So the Spark Cassandra connector just allows you to create RDDs from Cassandra.
Spark Cassandra connector creates RDDs.
Yep.
Well, I'll show you a code example in just a bit. So you'll see, like, it's pretty easy to create a table out of that data. So why don't let's see if we can get through like more of the stuff, right? The querying is not columnar based yet, so that's one room for improvement. But one really cool thing that you can do, there's 2 really cool things I want to highlight. One is that Spark SQL allows you to write custom functions like UDFs in Scala or Java, and so you can just register them and then run the query. This is a much easier process than if you've used Hive, like you have to write UDFs and like it's much easier, right? And the other nice thing is that you can get your SQL table results and easily feed them into other modules in Spark. Like you can feed them into ML-base for doing logistic regression and other things like that, which is pretty compelling. All right. So I said there would be a simple code example. Like, so this is the first line here. You see sc.cassandra table. This is how you would use the Spark Cassandra connector to get data out of your Cassandra rows. The GDOUT row is basically a case class in Scala, which is just a POJO basically with different fields. Then I can do .register as table, which will actually register that RDD of GDAL rows as a table, and it will use, it will look inside the structure of that object to figure out what the fields are. Then I can cache it, which turns it into, uses that efficient in-memory columnar store to store the data. Then I can run queries on it. Something to point out is that there is a collects at the very end. Spark is lazy, so nothing gets executed until you run a command that forces Spark to actually do the computation. And finally, the register as table is will be called register temp table. So it's a minor thing. So I did a study with the GDAL dataset. How many people know about GDAL? Okay. So this is GDAL is a global database of events, language, and tone. It contains kind of political events since 1979 across the world. 117 million rows with 57 columns. It's about 50 gigs. Depending on the query, you can do between half a second to 2.5 seconds. And the 2.5 second is where you're doing a grouping, some aggregation kind of thing. So not too bad for this much data. I'm sorry I didn't have enough time to compare this to some other things like Redshift, which I would have loved to do. So one point about caching. There's different ways of caching data. As I mentioned before, if you don't cache the data in Spark, by default, it will go back and reread the data from the source, which in our case would be Cassandra. Obviously you can do many things to speed this up, like use SSDs and stuff, but it would still be much slower than reading from in memory. So in Spark, you can cache any RDDs, and this will allow you to save it in memory and reuse it. However, for tables, I would say don't use Spark's. There's two ways to cache it. You can use the caching in Spark SQL, or you can use the built-in Spark generic caching for all RDDs. So you should definitely pick the SQL caching, because that way it will store the data in memory in a columnar format, and you get all the benefits of using things like dictionary compression. Spark will actually figure out the best compression algorithm to use for your data. It will use run length encoding if that's appropriate, that kind of thing. There's still a lot of work needed. In particular, it'd be great to have tachyon support for Cassandra. There are no indexes right now, so obviously it won't fit all use cases. But I do believe that even as it is right now, Spark, and particularly Spark SQL, gives you a pretty a pretty good query engine for your data in Cassandra, provided you have a general OLAP-like workload. And as I mentioned before, caching is very important. Lastly, when I say OLAP, I'm talking about your BI users running a few queries, and they can do this interactively. I'm not so much talking about the using Spark for interactive, kind of as a backend for web queries, although that might work as well. Thank you very much. Yeah. Yes.
Okay, my question is, does the DataStax Spark connector work with Spark 1.0?
Sorry, could you repeat your question? It's kind of loud.
Okay, does the DataStax Spark connector work with Spark 1.0?
Oh, 1.0.
Yeah, because I saw the documentation is only work with 0.9. I tried the 0.94, it's working.
I see. I am not. I would be very surprised if it did not work with 1.0. Yeah. Okay. Thank you. Thank you.
Okay. Thank you.
Yeah.
Do you have some examples that that can be seen on like GitHub?
Oh, I do have an example. I forgot to include a URL. I do have an example of querying the. I have a project in GitHub that sets up the GDAL dataset for Spark SQL and has some utilities for benchmarking. I can, you know,
Sure.
we can chat afterwards if you're interested.
Excuse
Yes.
me?
Okay, so Columnar looks like it's fitting more into the analytics.
Yes.
Yeah.
Yes.
Okay, fine.
Yes.
And then the descriptive is more like row-based.
So the.
I mean, it depends, right?
Yeah, I mean, I think most people look at like role-based is better for, you know, transactional like OLTP, you know, kind of stuff, and you know, the Columnar is better. But if you're talking about Spark anyway, like it's not a database anyway, so you know.
Now, what about for the fast communication part? I mean, why does Cassandra is so good for that? Just because the way it's stored, it can scale. It's I mean, fast injection, and then you know I mean, why is Cassandra so good for fast network or communication part, flow part?
Why is Cassandra so good for fast network?
Yeah, the injection, you know, like data injection.
Well, let me try to answer what I think your question is. I think Cassandra is really good at like real-time data like input, right? So you can keep writing to Cassandra, and it's very, very good at that. And if it's particularly good for, like, I would say it's much better than just Hadoop HDFS for writing data, because what happens if your worker fails and you need to rewrite some data? And Cassandra is very good. You can write over some existing data with no problem. In Hadoop, you can't do that at all.
Is it faster to read from HDFS or from Cassandra?
You know, that's a good question.
It's faster to read from HDFS or Cassandra.
So the question is it faster to read from HDFS or Cassandra? I mean, I think it largely depends on how what your schema is in Cassandra. I mean, I can pick so there's something called Cassandra file system, right, which is HDFS on Cassandra. If I store large blobs of data in Cassandra and I take advantage of wide rows, I think it can get, you know, pretty close or even better than HDFS. Definitely better latency.
Excuse me?
Does Spark store any state information in Cassandra? What happens if something bad happens in Spark and a node dies or something?
Okay, that's a good question. So what happens if data dies in Spark? So the way that the fault tolerance works in Spark by default is that Spark has what is called lineage, which means it remembers the steps that you took to do a computation. And so let's say that your computation started with reading from Cassandra. Then it's going to go back to Cassandra and read that data.
So it will replay the data.
So we'll replay the steps for doing the computation. But there's two ways to ameliorate. There's multiple ways to make it more, to shortcut that. One is that you can actually replicate data. You can replicate caching in Spark across like 2x. So if one node dies, then it's resilient to that.
Yeah, but then like in Storm, the way you can save the state, right? Can we do that? Like, can we save a state of a computation and then pick up on that later on?
Yeah, there's something called snapshots. I haven't played with them myself, but it's supposed to store the current state of your computation and let you pick up on that.
And I assume that's not integrated with Cassandra, right?
No. As far as I know, it requires HDFS right now.
Okay,
You know,
that would
so
be cool to have
it would. But I think the Tachyon though is a really good way. That way, like, you know, you can actually write data to Tachyon, and that way, like, it will survive process that, so you can, like, you know, you could play the data. But it's in memory, so it's lower overhead than reading and writing from, say, Cassandra or HDFS. But,
Excuse me?
yep.
But then it's after the process is done, right?
You can save it manually however you want. It's the snapshots is just a more convenient way. Well, snapshots actually save the state of your Spark application, so it stores more things than just your data. Which, yeah.
Excuse me? how much
Hi.
time, approximately how much time did it take to create the GDEL table in Spark?
Oh, to create and cache it?
Yeah.
Okay, so I have the data somewhere, but not like with me. It's in a different place. But it depends on your source and how you parse it. And like if it's from S3, mine was pretty slow because I was reading from S3. And the way that I was parsing it was kind of inefficient. I think it was like 10 or 20 minutes to load the whole thing. And I think there's a lot of room for improvement to that.
But then approximately it took a couple of minutes in order to create that table, or in hours?
No, see, it really depends on your source and how fast it is. I think if you were to use the right Cassandra schema with SSDs, it could probably cut that down a lot.
Okay.
Yeah.
Okay.
No, because Hadoop would be like 10 or 100x slower, which would not work at all.
Have you measured the impact on Cassandra for creating these tables in Spark? So let's say I want to load the entire column cache.
So you're saying like how heavily does it tax Cassandra?
What is the tax on Cassandra?
Right, so if it was like if you were reading from your cluster but also doing analytics, would it be impacted?
Yeah, I mean definitely it incurs a heavy read burden. I haven't actually measured the performance, but in reality, I would only expect to read the entire for most data sets, it's more like you would append to it over time. So in a normal case, I would only expect to read the new data, unless somehow an entire cluster failed and I didn't have anywhere else. So in the worst case, I would need to reread the entire snapshot in memory. Then that would be bad. But hopefully there's enough XJ and other things going on that
So you have enough replicas to make.
right, exactly, that's not a problem. But
So it's not unusual to query millions or billions of rows using OLAP on distributed servers.
yeah.
Like let's say Impala.
Yeah.
Are you saying that Cassandra could do that? Spark?
Yeah, I think Cassandra together with Spark will let you do that. It's just a matter of how fast it is. So I guess the way you look at it is that what I'm proposing, so you can directly read from Cassandra every time and do queries. That will totally work with Spark. It's just a matter of how fast you want that stuff. I guess what I'm saying is that if you spend a little bit more time to cache the data up front, then you can run a lot of queries over the same data set and be very fast.
Is that where Tachyon comes in as a piece of puzzle?
Yeah, well, you can do it with or without Tachyon. Tachyon just means that in case of failure, you can share the data across multiple Spark instances, and in case of failure, it's more resilient, which are good properties. Yeah.
So regarding snapshot,
Yeah.
before an action happens, we might have multiple transformations.
Yep.
So when we enable snapshot, are we going to snapshot every transformation, each step? How does snapshot happen?
To be honest, I haven't played with snapshots that much, but what I hear is that it saves all of your data. So,
Is it seems like every transformation?
well, I think it saves the current state of your data.
Right.
You
But
know,
there are multiple states, right? Because before you reach action points, you might go through multiple transformations. Each transformation is going to transfer data from one state to another state.
right. No, I think it just saves your latest state. But I'm not. I really played with it much, so I'm not really sure.
This method is called checkpoint.
Yeah, checkpoint.
So
Yeah.
it's